Sometimes the charm will get this.
We're going live on YouTube. We're live.
Hey, welcome everyone. It's the top of the hour. Let's get started. Welcome to our July NASA Night Sky Network webinar. It's hosting tonight from the Astronomical Society of the Pacific in San Francisco, California, and we are so excited to welcome our guest speaker, Dr. Brian Grefenstette from Caltech. And welcome to everyone who is joining us tonight on the live stream. We're happy to have you with us. These webinars are monthly events for members of the Night Sky Network, though we look forward to continuing the live stream online as well. We're happy to have you all here. So for information about the NASA Night Sky Network and the Astronomical Society of the Pacific, check the links in the chat that Dave is going to put in there. My name is Vivian White, and Dave and I work on the Night Sky Network. Before I introduce our speaker tonight, here's Dave Prosper with a few announcements.
Hi, folks. There's actually not many announcements today. Enjoy your summer vacation, as it were. I think everyone is melting. Hopefully you're staying cool. Nice tip from my dad, who spent the day in his garage. You can just take some ice, throw it in a cooler, and turn on a fan. That might help. Or just wear the ice, as my brother apparently did. Anyway, just wishing y'all a happy 53rd anniversary of Apollo 11, as I saw a tweet from NASA, and with Artemis 1 scheduled for actually has some launch dates now, a potential August 29th launch window, and then a couple of others after that every 3 days. We'll see how that goes. Good luck with that Florida weather in late summer. But yeah, what else is happening? We've been blaming technical problems on the solar storm. There's still a little bit of an aurora report here and there. So, hey, good luck to any one of you in the northern climates, northern areas. Maybe you'll get to see something tonight. I won't because of storms. What else we got? Oh, honestly, we're just going to see you at Alcon next week, Vivi and I. I look forward to seeing those of you traveling to beautiful Albuquerque, New Mexico, for several days of astronomy fun in the desert. Anyway, that's honestly it. It's just a chill day. There'll be a lot more announcements. There is a ton of announcements. We can't talk about them yet. They'll be in the August newsletter. Everything we wanted to mention is like, oh wait, no, embargoed. Oh wait, not yet. So anyway, take it away, Vivian.
Thank you so much, Dave. All right, for those of you joining us on Zoom, you can find the chat window, most of you already have, and the Q&A window at the bottom edge of your Zoom. If you're on desktop, feel free to greet each other in the chat window or let us know if you're having any technical difficulties there. Thanks for those of you who threw in the note about the chat not working. I think it should be working now. You can also always send us an email at nightskyinfo@astrosociety.org. But if you have a question for our guest speaker tonight, please type it into the Q&A window. That helps us keep track and know if we've answered questions. Sometimes they get lost in the chat. All right. Could you hit record on that one, Brian, and then I'll get started. There we go. Welcome, everyone, to our July webinar of the NASA Night Sky Network. This month, we are so pleased to welcome Dr. Brian Grefenstette to our webinar. Dr. Grefenstette's a principal mission scientist on the NuSTAR mission and a research scientist at the California Institute of Technology. He grew up in DC before coming out west, getting his BS in physics at Stanford University, as well as his PhD in physics at UC Santa Cruz. He joined the NuSTAR mission as a postdoc scholar at Caltech in 2009, 3 whole years before the launch, and has been down in Pasadena ever since. His science interests span almost 9 orders of magnitude in source intensity anyway, from studying radioactive ash from supernova explosions all the way to X-ray flares from the sun. He's an avid disc golfer, a gamer, a dad, and loves exploring the night sky with his friends, even in Los Angeles. That's actually how I found him. He mentioned he was an amateur astronomer, and I said, please come and talk with us. I think everyone would love to hear from you. Welcome, Dr. Brian Grefenstette. It's really lovely to have you here tonight.
Thanks for having me, Vivian. All right, so let's get the screen shared. All right, we looking good?
Fabulous.
All right.
Great.
All right. Well, again, thanks for having me here. As Vivian said, she got in touch, and I was excited to come give a talk to you guys. By the way, I talk with my hands, and if anyone sees my camera moving out of focus, let me know. When I was growing up, I grew up in the suburbs outside of DC, and my parents got me a little, 4.5-inch reflector. I had the full filter set, and so it was good enough to go out and hit Jupiter and Saturn, and you could see the moons move around Jupiter and all that kind of fun stuff. And then when I got into high school is when I sort of really started to get into astronomy. I did a couple of summers at the Naval Observatory in DC. And the science part of it was fun, but the big fun part was I got to actually help run a bunch of the star parties they did there. They have like a 12-inch refractor, which is 20 feet long or something like that. But the floor goes up and down. You have to go in and manhandle the telescope. And we got to take people up and really start to get a good appreciation for the night sky. So that was really my foundation in astronomy. I had a really great physics instructor. So when I decided I want to go out to college, I knew I wanted to do physics and astronomy. Stanford only has a physics department. So I did get to do a lot of work with Roger Ramani, who's there. He built a teaching observatory, fully robotic, so you can go drive around the sky. We got images of the crab, a high redshift quasar, all kinds of fun stuff. So that was sort of my college experience. And then I started building detectors. So I got involved in a group with Blas Cabrera and Roger Ramani, building really cold, like 100 millikelvin single photon detectors for optical astronomy, and putting them on the backside of a telescope so you can see high frequency pulsations from the crab and all kinds of fun stuff. So when I went over to grad school, I got into sort of the high energy astrophysics side of things. So the physics department at Santa Cruz does the gamma ray and X-ray astronomy, and the astronomy department there does all the optical stuff. So I got really involved in X-ray detectors, building gamma ray instrumentation. We're studying gamma rays coming from lightning, so we built devices to go fly around inside thunderstorms and all that kind of fun stuff. So that's when I started thinking of myself as sort of an experimental astrophysicist, and that got me down to Caltech to help work on NuSTAR, which is what I'm happy to talk to you guys about today. And it was really when I started working on NuSTAR again that I got back into doing the astronomy side of things. I'd sort of taken a break for a few years while I was doing the high energy physics side. And I'm really happy that I got back into it. And X-ray astronomy is a really fun field to be involved in because it's fairly young. We've only had really X-ray telescopes since the 1960s. And a lot of the times when you build a new instrument like NuSTAR, you get an entirely new view on the universe. And so that's why we're here today. NuSTAR is one of those instruments that was sort of a complete watershed moment in high energy astrophysics. So we hit our 10-year anniversary about a month ago, with first light happening about, 10 years ago, 3 weeks ago. And I'm going to tell you guys about, some of the science highlights with NuSTAR and sort of what an X-ray telescope is and how it might be different from things that you're used to using in your backyard or at a star party or something like that. So NuSTAR it's a small explorer. So this used to be the smallest thing that NASA launched into space. So these things are sort of $150 million, which sounds like a lot of money for most people, but for a space mission, that's very cheap. They're light, not very massive, and they're usually fairly targeted. So NuSTAR was the PI is Fiona Harrison, who you might know from chairing the decadal survey in astronomy, which I think you heard about a few weeks ago. So Fiona's been the PI of NuSTAR. She worked on other high energy telescopes before that on balloons, but she's really been our fearless leader for the better part of 15 years now. So I just want to put NuSTAR in sort of perspective for the NASA fleet of space-based observatories. So these are either missions that NASA flew or NASA contributed to. This is from Paul Hertz, who is the outgoing director of NASA Astrophysics, from one of his slides from a few years ago now, so it's slightly out of date. But the thing I wanted to sort of point out here was that I also feel like I got very lucky because I got into this field right during a very golden age of high energy astrophysics. So this starts in the late 90s with XMM and Chandra. These are flagship caliber observatories. So Chandra from NASA, XMM from ESA. They're very complementary to each other. They both launched in 1999, which is when I was a senior in high school. And then as you move into the aughts, so the 2000s, we had Swift and Fermi, which sort of brought even the high energy gamma ray sky into sort of a modern era. And as you get into the teens, you have NuSTAR and NICER, which is an X-ray observatory that's mounted on the space station. Now that we're getting into the 2020s, we have IXB, which is a polarimeter, which just launched this year. And then early next year, we have the XRISM mission, which is a mission from JAXA. All of these observatories work together, and they all give us a different perspective on what's going on in the universe. So we've really been very, very lucky that all of these missions have been flying at the same time to really get a good feel for what's going on across the high energy sky. So just to put NuSTAR in perspective, so here's the electromagnetic spectrum. So if you are an optical observer, this looks backwards to you because the photons get lower or shorter wavelength going to the right. That's how X-ray astronomers draw things out. Energies increase to the right. So Chandra and XMM covered that sort of soft X-ray band from a few hundred eV to around 10 keV. keV is it's an X-ray astronomer unit. A visible light is a few electron volts. When you get 1,000 times that, then you start to get into the X-ray regime. And typically, a lot of the X-rays that are produced in the soft X-ray band are things that are coming from atomic transitions. So just like neon, when you pass a current through it, you get a particular color. You get colors associated with shocking hot material in like a supernova explosion or in the material between galaxies. And so we see very specific colors that are associated with various elements where the electrons are jumping up and down. And a lot of that occurs in the soft X-ray band. And Chandra and XMM have been excellent observatories for covering that part of it. NuSTAR extends that horizon to higher energies. So we start at a few keV and we go up to 80 keV. So this is, as you can see, a much broader bandpass, even though it's drawn, it's a log plot here. So it's drawn about the same width as what you have on Chandra and XMM, but it really extends up to the part where you're seeing the hottest and densest material in the universe, high energy electrons that are accelerated in gamma ray bursts and supernova explosions. All of this stuff, all of that action is happening in the hard X-rays. Now, there were observatories in the hard X-rays before, but NuSTAR was the very first hard X-ray focusing telescope. So you're sort of going from a regime where you know that there's something interesting going off in that part of the sky to it's going off at that star or that black hole or in that galaxy. And that's really the key new technology or the key new enhancement that NuSTAR brought to the table. So just to get us some perspective on this, here's a great infographic from Wikimedia. So this shows you sort of the electromagnetic spectrum, again, backwards if you're an optical astronomer, but correct way for an X-ray astronomer, going from low to high frequencies. And this sort of gives you a scale, a feel for the scope and the size of the photons that are coming in. When we think about a microwave, we're thinking about, we sort of know sort of macroscopically, that's fiddling around with water atoms. Radio waves are, the size of your car kind of thing. When you get to the ultraviolet and the X-rays, you're talking about things where the wavelengths are closer to the atomic scale structure, and then gamma rays for the nuclear structure. The bottom panel is the thing that's sort of is really the thing that we want to get out of the high energy X-rays, and that's showing you the temperature of an object that's mostly emitting that light in that bandpass. So if we take something like the sun, it's producing a few thousand degrees. It's producing mostly infrared and visible light. If I crank up the temperature on the sun, I get a bluer star, and that moves the peak of the emission out to higher energy. And if I increase the temperature on gas even higher, I can get to the point where I actually make ultraviolet and X-ray light. And so this is typically when you get to temperatures of a few million degrees, 10 million degrees. That's when you're really getting a lot of that X-ray emission to come through. Now, there's also all kinds of other things where you've got electrons hitting things when they're traveling at roughly the speed of light will also make X-rays and gamma rays. So we'll get into some of that a little bit later. The last thing I wanted to point out on this slide is the top panel, which is sort of the where the light actually gets through down to the surface. So what can you do from the ground? And obviously you can do infrared, some infrared and some optical, well, definitely optical observing from the ground. Once you get into the ultraviolet and the X-rays, all of that radiation is actually blocked by our atmosphere. which is great. That means we don't get cooked when we're here on the surface. Similarly, when you get down into the microwaves, you can't do that from the ground. You have to go to space to do this kind of science, which is why you've got a mission like NuSTAR. When you want to open a new horizon, you really have to put something new in space. All right, so here is NuSTAR. So I thought it'd be useful to go through sort of the practical anatomy of an X-ray telescope. Right, this doesn't look like a telescope that you're used to seeing. There's no big mirror. There's no it's hard to see where the X-rays are actually moving in the sky. So for X-ray observatories, you sort of have sort of three key components. So one is the X-ray mirrors themselves, and we'll talk a little bit about that in a minute. Like you need special mirrors and actually focus the X-rays. You can't just use a reflector like you have on the ground. You need a long focal length. X-rays don't like to get focused. You can't put them through a lens because they get completely absorbed. So you have to do something else. You need a long focal length. NuSTAR has a 10-meter focal length. Chandra and XMM are about 6 meters. Most of the new observatories out there are between 6 and even 20 meters for things that are being proposed now. So you really need a long focal length. So these things are macroscopically big compared to what you might think of for like a rocket fairing or even the space shuttle. And then down at the other side, you've got X-ray detectors. That's where we actually, detect the X-rays themselves. And these are also different than what you actually would think of, or you might have experienced with for an optical telescope, where you've got sort of either a photograph or a CD. These are actually single photon counting detectors. The X-ray sky is pretty dark, so we don't have millions of photons, unless you're pointing at the sun, hitting our detectors. So we can use specialized technology to actually get that information out. And down there behind the detectors, that's where we actually mate to the spacecraft. So just on X-ray mirrors, like I said, there's you need special mirrors. Let's see if I can get this to play. There we go. So if you just throw photons at a glass surface, they just get absorbed and scattered away. They don't do anything as far as the focusing goes. So what you need is a conical mirror like this. This is from Chandra and the Chandra Space Science Center. Here the photons come in and they have a grazing incidence deflection. So they only deflect off each of those mirror surfaces by about 1 degree. And that drives you to a very long focal length. So in Chandra, they had a few shells that were used to actually collect all of the photons, and they focused down on their detectors, again, 6 meters away from where the optics are. NuSTAR's got a few more shells than that. This is one of the enabling technologies. On the left, this is one of the X-ray optics as it's being built. These things are about 35 centimeters across. They are very heavy. There's 133 shells. Each shell is made of glass, and each shell has a special material put on the surface called a multi-layer coating. So this is similar to what you might have in your to silver a telescope mirror if you're building a telescope for optical astronomy, or anti-reflective coatings for UV cameras and this kind of thing. So the multi-layer coatings are really the thing that give these mirrors their high energy X-ray reflectivity. And there's a lot of them because you don't get very much effective area per each little segment. So you've got to build up these really big optics that are very heavy to actually do the astronomy that we want to do. On the right, we have the imagers. So these were built downstairs here at Caltech. And these things are made of cadmium zinc telluride. They're a single piece of crystal. When a photon comes in or an X-ray comes in, it hits the crystal, turns it into a bunch of electrons. You can then read out all of that. Each detector is mated to a custom circuit behind it, so every pixel has its own set of readout electronics. And this lets you basically get a video stream of information coming from your detectors. Every photon that hits the detector, we know where it hit, we know when it hit, and we know what X-ray color it had. We know what the energy the photon has. So we get a video stream of information coming from these detectors. And so, all of this stuff are things that you really need a lot of people working on these missions for. So I mentioned Fiona is the PI. The detectors were made at Caltech. The optics themselves were made at Goddard in Maryland. The coatings were developed by the Danish Technical Institute, DTU, in Denmark. And then our JPL manages the mission and does a lot of our media outreach now. And we also there's a wide science team who really helped make NuSTAR a really, really successful mission. So it really takes, we say it takes a village. It took a lot more than a village to get NuSTAR off the ground. This is how you get off the ground. So when you've got a small mission, you sort of need to fly on a small rocket, or at least that was true before SpaceX came along and gave us Falcon 9s. NuSTAR was designed in the mid 2000s, and it was designed to fit in a Pegasus launcher. So the Pegasus you can sort of see on the bottom right there. This is effectively a modified cruise missile. It was originally made by Orbital Sciences. Orbital has been bought by Northrop Grumman, so they own the Pegasus now. I think we're just about done with the last Pegasus launch, although Virgin Galactic is working on a version of this called Space Launcher 1, where it launches a bunch of small sats. Your entire observatory has to fit in the nose cone. So if you sort of see on the bottom right image, there's that little metal band. Everything north of that is the observatory. And on the left side, that sort of shows you what this thing looked like when it was all put together in Dulles, Virginia. This is the spacecraft on the bottom. You can sort of see the X-ray optics. The solar panels are wrapped around the thing, but it's only 2 meters. I'm about 6 feet tall, 6'3". And so this thing was just a little bit taller than I was when it actually launched. On the top right, you can see it getting placed into the fairing at Vandenberg Air Force Base. And the reason that we want, well, first off, again, there were no small launchers at the time. But the other thing that that launching from an aircraft allows you to do is it allows you to get to wherever you want to go in order to do your launch. You don't have to launch just from Vandenberg and just from the coast of Florida. But you can actually go out and launch in the middle of the South Pacific, which is actually what we did on NuSTAR. And I'll get to why in a few minutes. If you haven't seen a Pegasus launch, they're pretty spectacular. This is not the NuSTAR launch. NuSTAR launched at 4 o'clock in the morning local time. So we didn't have a chase plane. This is actually a solar observatory called RESI. You can see the Pegasus strapped to the bottom of the L-1011 as it takes off. The pilot says 3, 2, 1, drop. And then you have the longest 7 seconds of your life until the rocket ignites. There we go. And your payload goes off into space. Drop to orbital insertion was about 5 minutes. So it's a pretty fast launch sequence. So it was really one of those things that was, we were in a big, lecture hall at Caltech, waiting for the drop call, and everyone cheered when we saw basically one little last picture of the thing falling out of the belly of the L-1011, and that's the last time anyone saw NuSTAR. Now, I told you earlier that you need long focal lengths. And then I just told you that the telescope's only 2 meters tall, right? So how do you square that? And the answer is a lot of amazing engineering. NuSTAR is a transformer. So this is what NuSTAR looked like. This is a simulation of what NuSTAR looked like after it was in space. So we don't have a GoPro floating around. It shows you what the thing looks like. So the instrument went up. The solar panels deployed almost immediately because we are in low Earth orbit. So we go behind the sun or behind the Earth. Quite often, so we need to keep the batteries charged. And then once we got up there, Northrop Grumman or Orbital took a week or so to make sure they knew how to drive the spacecraft. Everything checked out fine. That's when we actually did the deployment, which is the video that I'm going to show here. So there's the optics. There are the detectors sitting below them. There's a canister on the other side, and there's a single motor that starts driving out what we call the mast. Now this mast is, each one of these bays is about 4 inches on a side, and each of these little mandrels, or each of these little bars here is really small. It's so small you could never deploy this on the ground with any mass on it because it would fall apart. But in space, there's not a lot of relative gravity, so you can deploy it just fine. There's a single motor down at the bottom. This whole thing took about 15, 17 minutes on the ground. I was there in the operations center. All we got, again, we don't have any cameras to show us what's happening. All we got was the current blip every time one of those little bays locked together. And we're counting to make sure we got all 17 or 33, however many there were. So it was a very stressful day. We'd gotten through launch. We'd gotten through in-orbit checkout. We were actually getting the instrument deployed. And now we've actually got a fully functioning observatory. Now, one thing that's kind of interesting about this configuration is you've got this mast hanging out there, and we go around the Earth. So we go around the Earth once every 96 minutes, which means we go in and out of daylight once every 96 minutes. And when that happens, the mast actually has a little thermal motion associated with it. And if we were only, a few meters long, that wouldn't be a problem. But, 10 meters is the length of a school bus. And we want to keep these things really well aligned to make sure we get not very blurry images. And so you can see on the top here, there's actually a couple little black boxes there. And those are actually laser diodes that are shining down onto the focal plane bench. There's a couple of cameras down, infrared cameras down at the bottom. And what that does is allows us to actually reconstruct the full three-dimensional motion of the spacecraft in real time. And because we have a video stream from our detectors, we can take out any motions associated with the mast moving. So we don't have any blurring associated with the mast moving around, even though it does move quite a bit as we go around the Earth. Now, X-ray observations are fairly long. We typically look at a target for half a day. So we talk about tens of kiloseconds. We don't even talk about hours. And so most, the shortest thing we do is about 20 kiloseconds long. So we have many, many orbits per target where we actually are going through this thermal stat. So that's kind of the overview of the instrument itself. This is what we get out of it. This was our first light image 10 years and 3 weeks ago. And the top right is sort of the conceptual picture of what we had before. So these were these non-focusing observatories that could kind of tell you, well, there was something interesting going over here. In this case, we're looking at Cygnus X1. That's where it is in the sky. So it's in the middle of the Cygnus constellation near Vega. So if you go out probably right now, you can go find it in the sky. And on the bottom right is actually the focused image of what we actually were seeing with NuSTAR. So this is a black hole. It's a point source. That's what the point source used to look like, this big blob on the sky. And now we know, okay, we could focus it down and get that really nice image. This is another example of what we can get. This is the galactic center. So Sagittarius A star is, you probably have heard about from the Event Horizon Telescope observations over the last couple of years. This is the galactic center. This is the big black hole in the center of the Milky Way. The top is sort of the best hard X-ray image we had before from Integral which is a European observatory of what the galactic center looked like. The bottom is a zoom in of that cyan box, sort of showing that now we're resolving all of these targets into point sources. We can see Sag A star there. That's kind of the cloudy thing at the bottom. This is colored by the X-ray hardness. So these are sort of giving you a metric on how hot or cold these sources are. And there's about 500 sources in this field that we didn't have hard X-ray observations of before. As we move sort of further out, we can look at nearby galaxies. So this, I think I'm probably covering this up on the top right, but this is M31, which everyone knows and loves. This is a GALEX image in the ultraviolet of M31. And this little inset here is the NuSTAR image of all of the X-ray sources in this galaxy, in this patch of sky. So again, before you sort of know that there was a blob over there somewhere, and now we can resolve all of these targets and really get a feeling for what they're doing at the hard X-rays. Now, for this kind of observation, we can work well with Chandra and XMM because they have a better resolution than we do, and we can tie together the soft and hard X-ray measurements to really get a good feeling about what these sources are. So that big blue one on the right was actually a pulsar that was discovered in this NuSTAR observation to actually be pulsing. So it's pretty cool stuff. Moving even further away, we can look at other galaxies. So this is a galaxy where we see two ultraluminous sources in the galaxy. These are very, very luminous X-rays coming from somewhere that's not in the center of the galaxy. Most galaxies have something called an active galactic nucleus, which is a giant supermassive black hole. And again, this is something where NuSTAR can resolve out these two sources and tell us that they're not actually coming from the center of the galaxy. I'll get back to ULXs and why that's a pretty exciting new field in just a minute. So the first 10 years of NuSTAR have been amazing. So we've had 1,130 papers over 10 years, 60 PhD, so 1,130 was as of yesterday. So I just looked these all up. 50 PhD theses, it was 59. Our grad student, Sean Pike, just defended this week. So congratulations to Sean. NuSTAR has gone through 55,000 orbits of the Earth. And we've done over 3,500 science observations. So it's been incredibly productive for a very small mission. Right? We added it up the other day. We really think we run NuSTAR on about 4 or 5 FTEs. That's full-time equivalents. So that's a couple of part-time people, a couple of full-time people. it's a pretty tiny mission when you compare it to something that you might have like Hubble, where there's 4 times that many just working on public outreach. So we're our job is to keep NuSTAR really, really productive and a useful resource for the community. So I'm gonna talk a little bit about some of the science highlights from NuSTAR. Obviously, with 1,100 papers, there's absolutely no way I can do a survey of this. So I'm gonna hit some of the big watershed moments, the things that where we did the observation with NuSTAR, and we say, okay, this is there's no other way we could actually figure out what's going on in these sources. So if if any of my friends are on, there might be, if anyone's got a favorite source and I don't talk about it, my apologies. So the first thing I want to talk about is black holes. So this is what a black hole looks like, right? There's nothing there, right? It's black. So black holes, they are the cores of collapsed stars. We think they're the cores of that live in the center of many, lots of galaxies. We know that we've got black holes merging from the LIGO measurements of black holes spiraling in and making gravitational waves. But when they're sitting there by themselves, there's absolutely nothing you can do to see them. However, once you start to feed them, you got a wealth of information about a lot of interesting physics about what's going on in the source. So this is an artist impression. This is from Robert Hurt, who's at IPAC, who's a fantastic artist and scientist. You probably have seen a lot of his work, you just never knew it. This is an example of what a supermassive black hole at the center of a galaxy might look like. So you've got all of this material swirling into the black hole. We call this the accretion disk. You've got the black hole there in the center, and the black hole is still black. You can't see it. You've got a jet coming out that's producing high energy X-rays. And there's also this big torus of gas that's in the galaxy itself. And so one of the things that NuSTAR lets us do is peer through all of that gas and dust. For Chandra and XMM, there are some of these sources where you simply can't see them because they're shrouded in the center of these galaxies. And so NuSTAR hunts these black holes when we look at parts of the sky that are completely devoid of other X-ray sources. We're looking for these missing black holes that are in the centers of galaxies. Now, a lot of the accretion disk itself has a lot of interesting physics in it. And that sort of leads us to our first point here, which is there was this argument in the community for decades before NuSTAR launched. And it had to do with whether or not we could figure out what's going on with this black hole at the center of the galaxy. So when you have soft X-rays, which is here shown by the red and orange bands on the right, you see this emission from the accretion disk. It's hot, so it's glowing in X-rays. And then you see this emission from iron. So iron is one of the elements that has an emission line in the NuSTAR band at 6.5 keV. And we see that there's some distortion in the iron line coming from these galaxies, and we didn't know what was happening here. And there was sort of two camps here. One was, okay, you're seeing something really interesting, which is the top one, which is you're seeing gravitational effects distorting the iron line as it orbits in close to the black hole. And if that's true, we should have this high energy excess. This iron line comes from reprocessing emission in the accretion disk. You get that emission comes back out as this high energy Compton hump. On the bottom is the other option, which is that, I told you there's a bunch of gas and dust around. Maybe it's just a bunch of gas and dust moving around at different velocities. And so it's absorbing that light. So it's making this thing look like a broadened iron line, even though it's just something more prosaic. It's just the dust in the galaxy. So we went and looked, and this is one of the first things NuSTAR saw. So this was NGC 1365, which is active galaxy. The blue data points are what you get from XMM Newton, and it had this big iron line, and they couldn't tell the difference between whether or not it was gas or gas obscuration or this gravitational distortion of the accretion disk. And immediately you throw down the data and you're like, okay, that was too easy. Right? We plot the NuSTAR data and you see this giant hump coming out at high energy X-rays. So this was the first NuSTAR paper, came out, I think, in January 2013. First paper in Nature. It was fantastic. So we sort of knew immediately that it was a gravitational distortion that was causing this broad iron line down at low energies. Now, that's interesting because you actually get to go then do physics with this. So black holes are sort of famously the most interesting and simple objects in the universe. They're parameterized by exactly two things for most astrophysical black holes. One is their mass, and another one is their spin. Now, it's not actually spin, right? The black hole itself isn't sitting there spinning around, but it has angular momentum, which rotates space-time as you go in towards the event horizon. And when this happens, it can actually distort the accretion disk. So I think people have heard about this concept of the event horizon. There's a similar, where light can't get out anymore. There's a similar concept where you have the innermost stable circular orbit, which is the last point where you can put a little particle and have it orbit the black hole and not fall in. And depending on the spin of the black hole, that can actually move that innermost stable circular orbit in and out. And when you do that, you see things that you can actually observe in the colors that are coming from the accretion disk. So if I have a black hole that's spinning sort of anti in the direction of the accretion disk, I see where the innermost stable circular orbit recede, and I get a nice sharp iron line. If I make it spin really fast, then I see much more gravitational distortion. And there's an entire field of science now that just goes and uses NuSTAR with other observatories to go try to study these phenomenon and try to get a good measurement of a large number of black hole spins. And the fundamental reason you want to do this is because that tells you about the evolution of the universe. As black holes grow up, the galaxies merge together. And if the two black holes get their mass mostly through mergers, then you expect them to have sort of low spin. If the black holes are sitting there getting most of their mass from accreting stuff, so eating material, then you expect them to have very high spin. And so this is actually one of the things we've been doing over the last 10 years, is trying to build up a large catalog of black holes to get a feeling of what their distribution of spins are. Now, this isn't a question NuSTAR is going to answer. We sort of need the next generation of telescopes. We can do this for maybe a dozen sources in the sky that are supermassive black holes. We need to do it for hundreds to really answer that question. But now we know that that's the question we need to ask because we have these observations from NuSTAR. So another thing that we can study and sort of instantly see, okay, there was something interesting there, was feedback from these massive black holes. As they're eating material, they spew out jets and they can spew out winds. So a wind is sort of like you imagine it's sort of blowing off material from the accretion disk because there's so many X-rays coming through. And that material can move outwards at like 30 or 40% of the speed of light. And when that happens, you get this thing called a P Cygni profile. And these things happen right at the upper bound of what XMM can do. So if you look at the blue data points, if you only have those, they just kind of fall off the top of the curve and you don't know that they come back. And so once you have NuSTAR, you have all the orange data points, you have the high energy side, you know what the continuum looks like, immediately you know this is a P Cygni profile, and you can measure the velocity of the outflowing wind. This is important because that impacts star formation in galaxies. We know that there are old galaxies and young galaxies, and we want to know why and how are they making more or less stars. And this might be actually one of the clues to figuring that out. So there's that. And finally, we can do this for black holes in our own galaxy. So these ones are more dynamic. Supermassive black holes are more or less static on the lifetimes of graduate students, which is sort of the important length scale here. Stellar mass black holes, this is where you have a black hole maybe 5-10 times the mass of our sun. They orbit big stars and they can actually accrete material, and they can vary on very rapid timescales. So here's a simulation from the Goddard Space Flight Science Visualization Studio showing the black hole is sort of accreting material from its companion star. That material is flowing into an accretion disk and flowing onto the black hole. And these things are dynamic. They have orbital timescales. They've got fluctuations in the accretion disk. They go through giant outbursts. You actually get a really good chance of studying very extreme physics with material at very high density and temperatures that you just can't do on the ground. So this is, again, one of the things that we're doing with NuSTAR. It's been a really fantastic journey to sort of study these things. So that's black holes. I'm going to talk now about sort of one of the black holes were sort of one of the things that we sort of knew that we wanted to study. I'm going to talk about one of the things that we didn't know was NuSTAR was going to be super exciting about, and that's ultraluminous X-ray sources. So these are sources that are in galaxies. This is M51, where they are not the center black hole. They're something else in the galaxy. And for a long time, they were a sort of an interesting topic because we know how far away they are, so we know how bright they are. And there is sort of a global diet limit on how bright things can be in the X-rays. This is called the Eddington limit. And this is a simplified version of it. But you basically have material trying to fall into the black hole, and you have radiation that's trying to push to get out. And that basically results in some pressure. And so there's a balance condition called the Eddington limit, where you've got a luminosity beyond which you sort of can't get any more material in, which means then you can't get any brighter, right? That's the brightest the thing can be. And because we know how far away these things are, we know that ULXs are this unit of 10 to the 39 ergs. Now that's an interesting number because that's either sort of a 10 solar mass black hole, something 10 times the mass of our sun, eating at exactly this Eddington limit, or 1,000 solar mass black hole eating like 1% of the Eddington limit. I mean, when we look at supermassive black holes, they're typically at a few percent of the Eddington limit or even lower, like our black hole is. And so for a long time, people thought, okay, these ultraluminous sources, they are intermediate mass black holes. These 1,000, 10,000 solar mass black holes, they have to exist. We've never been able to find them. We have supermassive black holes, 1 million times the mass of our sun, stellar mass black holes, 100 times the mass of our sun, neutron stars, way lighter. This thing in the middle is sort of the missing link. And so there was a big discussion for a long time that, okay, that's what the ULXs are. So a supernova went off. There was a supernova in M82, which is the Scar galaxy. It went off in 2014. And this was super exciting because it was the closest Type 1a supernova that had gone off in 30 years. We were all in New York at one of the New York NuSTAR science team meetings. We were arguing about when we were going to see it in the X-rays, and everyone pointed their telescopes at M82 for like a month. Now, we didn't see anything from the supernova, but this black hole has 2 ULXs in it. And I have a friend of mine who really likes studying this, all the dynamics of how black holes change. And so he went and he looked at the time signatures of these black holes, and he says, oh, okay, that's weird. They're pulsing. One of these things was pulsing, and it was pulsing, so you could sort of see it like a lighthouse, and you could tell that it was going around something else because you could see the pulses change over time. So it's pulsing twice a second, and it was orbiting something else. Now, black holes can't pulse. Right? There's no surface there to make the pulsations happen. So this had to be a neutron star, and this thing was emitting light at 1,000 times or 500 times brighter than it should have been from the Eddington limit. So this is kind of what we think was happening. You've got the companion star, it's feeding material in, it swirls into this neutron star that somehow is accreting a lot of material and is beaming out this very, very bright light throughout the universe. This has kind of been one of those things that no one expected these things, right? There's a good Isaac Asimov quote, which is the most exciting phrase in science is never eureka. It's, that's funny. And this is definitely one of those moments, right? Neutron, studying these ultraluminous pulsars we found dozens of them. They're ubiquitous in the galaxy. They could represent all of the ULXs. So these things are not 1,000 solar mass black holes. They're 1.5 solar mass neutron stars. And how they do this, we don't know. This is something that we're still arguing back and forth about quite a bit. So the last sort of main science highlight I want to hit was how do stars explode? And this is something that we did design NuSTAR to go look at. On the left is our sort of physics, what I do when I teach astronomy, picture of an onion shell of what a massive star looks like as it's approaching the end of its life. You've got hydrogen on the outside, that's burned to helium. You've got oxygen, carbon, neon, magnesium, all that stuff inside. And then you've got the iron core, right? Stars are nuclear reactors, right? They're nuclear engines. They're fusing material together. That material releases heat, and that holds up the gravity of the star. Once you get to iron and you try to fuse iron into heavier elements, iron that takes energy out of the star to fuse together. And so once that happens, this runaway process starts to occur, and the star collapses down and then explodes in a supernova explosion. that's the story. Doesn't work. If you go do your, I have friends who try to blow up stars in their computers and they can't get the stars to explode. So you have to put in something else. You need to put in some fluctuations in order to make this happen. And the reason is sort of, you can sort of think about this like a pressure cooker, right? As the thing's collapsing down, all of that material is getting really, really compressed in the center. You're making really, rich high atomic number nuclei, gold, titanium, all of that good stuff. That's making neutrinos that are trying to get out, and it sort of hits a shock and it gets stuck. And once you allow for turbulence on the surface, this is what the top thing looks like. Then it's like having the pressure cooker and poking a hole in the top. The whole thing blows apart once you get one of these bubbles forming as it bursts out. And that can be a way that you can actually get the star to explode. The other way you can do it is you can have the core spin really fast. So this is another simulation of a stellar core where you made a neutron star in there. It has high spin, high magnetic field, and that's shooting material out the top and bottom of the neutron star, and that's the thing that blows up the star. So this is sort of an open question, and there is sort of a holy grail in high energy astrophysics for how to actually go figure out what's going on, and that's radioactive ash. So down way in the core of the star, right where you sort of have the last layer that is going to get blown away, and everything else is going to collapse into either a neutron star or a black hole, you make titanium-44, which is an isotope of titanium that's unstable. So it doesn't like to stick around for very long. And it splits into scandium and then calcium. And when it does that, so this radioactive decay happens, then you get gamma rays that come out. So one at 1100 keV and then two X-rays at 78 and 68 keV. And you have some positrons that also come out as well. And NuSTAR was actually built specifically to go find where these 78 and 68 keV photons are being produced in a supernova explosion. So enter Cassiopeia A. Cassiopeia A is one of my favorite supernova remnants. I wrote the paper on NuSTAR on this, so I sort of have to say that. It blew up in the 1680s, so it's fairly young. Titanium has a half-life of about 60 years, so you need to look at a young nearby supernova. And what we're looking at here is all different colors of X-ray light. And we can decompose all of these colors to tell us what the different elements are doing. So in red here, this is from the Chandra Observatory. You've got iron, so that tells you where the iron emission is. Green, you've got silicon and magnesium. Gold is sort of the continuum X-rays that are coming out. And the blue is the new emission that we had from NuSTAR. So anyway, we can take these images, and they look beautiful. And you can decompose them into those different components and say, okay, what looks like the other? So before launch, I still have a simulation on the wall in my office. We assumed that the titanium would look like the iron. The iron is produced where the titanium is produced. They should look the same. We'll find out it'll be over. The silicon and magnesium has this jet-like structure. So it's like, okay, well, that's another option. That it was actually the jet explosion. We should see it going in the silicon and magnesium direction. The right is what we actually saw. And so we were this took about 2.5 months of observations to actually find where all of this radioactive ash is. Because our detectors are very sensitive to the color, we can actually do a 3-dimensional reconstruction of what's happening at the inside of the star. And we know the radioactive titanium is not in the same place as the silicon and magnesium, and it's not in the same place as the iron, and it's not sort of this big uniform explosion. So this was really the first evidence that these bubbles, that simulation that I showed you before, were actually happening. This has to do with neutrino heating in the center of the supernova. These are big blobby structures. It was really a fantastic result. And NuSTAR, it's only because we had really good detectors, we had the imaging that we can actually go localize where all of this emission was taking place. So that sort of brings us to the next 10 years of NuSTAR. So NuSTAR is great because there's no consumables on board. So we don't have any gas pointing us around. We use magnetic torque rods to look around the sky. We just were approved by NASA through 2025, so that's great. So NASA takes a look at all of the operating missions every 3 years, and we are basically entirely a guest observer facility since the prime mission ended in about 2014. NuSTAR was only designed to last 2 years, And that allowed us to do all of that core science that we wanted to do, the black holes, the Cassia observations. And ever since then, we have basically been a community resource. So the way high energy astrophysics works in the US is people apply to say, I have this great idea to go point NuSTAR at something. We have a time allocation committee. It's a bunch of scientists who are not on the NuSTAR team. They sit down and they sort of grade all of the proposals, and then they figure out what we're going to do for the year. We do this every year, so we always stay very fresh. We're very agile to try to address what the community actually really wants us to do. We've had amateur astronomers write proposals. We've had high school students write proposals that have been successful. This is, it's really one of those things that X-ray astronomy is very egalitarian. You can, and I do most of my work on a laptop. You don't need your own telescope. You don't need a supercomputer. We provide, all of the code to analyze the data is open source. All of the data is free, or open source as we can make it. All of the data is freely available at the High Energy Astrophysics Archive at Goddard. And it's really something where, our job is to make sure that all of the users and observers are doing great things with NuSTAR. And then we're very excited to see where we go in the next few years. We're starting to do observations with JWST. CRISM is launching next year. It's going to be a very exciting time for NuSTAR over the next 10 years. So if you want to keep up with NuSTAR, so nustar.caltech.edu is our main page. So we post sort of little news articles there. When we do image releases, we do that. Most of that is written just by a few of us. So if you see an image there, it's probably done by me. The JPL, we use the JPL public media and outreach groups, who are fantastic. So there are occasionally news releases at JPL, so you can go there. NASA Universe is the official NASA account for all of the observatories. At NuSTAR Science is the unofficial NuSTAR account, where we sort of highlight a bunch of different astronomers at different career stages. We just had the NuSTAR 10-year anniversary meeting. So on Twitter, you can find that at NuStarX. There was some very dedicated person who, not me, who was going through and live tweeting the entire meeting. It was fantastic. Yeah, so I think that is where I'm going to wrap up. So I would love to do some Q&A. I see there's a couple of Q&A topics coming into the chat, but I'm going to hand it over to Vivian to sort of see where we're going to go with that.
Brian, that was fantastic. Thank you so much. I learned a ton. Thanks for keeping us updated. 10 years is kind of amazing for a relatively small scale project. I'm really impressed. I'm sure it doesn't seem small scale if you've been working on it for 13 years.
Well, no, it's very small scale, and it's always, it's one of these things where NuSTAR is getting cranky. So we have a lot of, there's a lot of effort going into making sure that we do things the right way to make sure the observatory lasts as long as possible.
That's great. There was a really cool question from Gregory here, who is asking about computer simulation and how we know that we're not introducing bias when we're programming what we think we might see. How could you just elaborate on how they do the computer simulations, especially of dying star? Would be really interesting.
Sure. So there's actually so the fun thing about science is that the best feeling you can ever have is proving your friend wrong. And so there are lots of different groups that are doing all of these simulations. And so especially for the supernova explosions, there are groups at a lot of the various big government labs that are doing supercomputer simulations. And those are all, they check each other and they make sure that they're all getting they're starting at the same place. And then they are tweaking, the physics a little bit. So you're always sort of aware that you're introducing your own, we call it observer bias, right? Especially when we're doing, spectroscopy. A lot of the stuff that we do with NuSTAR, we don't see the details of what's going on. We're sort of looking at a point source, looking at the colors that come out, and we're always starving for information. So we're always aware that there's stuff that we could put into the analysis that might not be there. But that's why we have all of our friends. That's why we do the peer review process, is to make sure that all of that gets caught before it gets, it's not released as fact. These are all things that people have to constantly revise.
Really cool. Maybe if you want to stop sharing your screen and we'll just show you.
Yeah.
You've got those links now. Definitely follow them on Twitter. It'd be exciting to see all of the updates as they come along. Cook is asking, is NuSTAR in low Earth orbit? And if so, how do you overcome any atmospheric drag and orbital decay?
Yeah, so we are in low Earth orbit, and we keep our fingers crossed. So NuSTAR has we don't have any thrusters. We basically just change our direction using magnetic torque rods. So it's something that we constantly are aware of, and the atmospheric drag changes over time. So as the solar cycle comes and goes, the Earth's atmosphere puffs up and dies down a little bit. So all of these aurora that people are so excited about this week, we really don't like them because it means the atmosphere is going to puff up and slow down NuSTAR. So that's probably the thing, either running out of NASA money or coming to the atmosphere is probably the thing that's gonna bring NuSTAR down eventually. Certainly the instrument will come down at some point. We're not going to be space junk. But if we get through this solar cycle, we've got another 10 years or so on orbit lifetime. So it's something that we're really we are constantly sort of paying attention to. But it also brings up a point, we're also constantly paying attention to other people in space. So especially with the proliferation of all of the CubeSat constellations, every week we get an update of, we might get hit this week or hit that week, and so there's nothing we can do about it. So we sort of point the narrow end of the telescope if there's ever a close approach. There hasn't been for a few years, but we're constantly getting updated on all of that stuff. So space traffic as well as space weather is always an issue.
It's like having your kid out in the world. Just good luck. Yeah. And you talked about it being NASA certified through 2025. How much longer do you think it might even last, if barring something hitting it? Yeah,
so the instrument itself is working fantastically well. So because we're in this equatorial orbit. So one bad side about this is I've never seen NuSTAR myself. So if you're I need to go to Costa Rica or something like that, and you can see it fly overhead. But because we're in that orbit, we don't go through the radiation belts. There's this point in sort of off the coast of Brazil called the South Atlantic Anomaly, which no one's ever heard of, but it basically is a point where the radiation belts dip down in the atmosphere, and it's a huge radiation background. And so if you fly through that a lot, then your parts decay and all that stuff. But because we're at this 5-degree inclination orbit, we just skim the top of it every couple of orbits. So the instrument itself is gonna, should work fine. Where's wood to knock on? But we're, because we're a small mission, everything's kind of single string. So we have one version of all of these components. We don't have any backups for a lot of these things. But as of now, we could easily go another 10 years and be fine.
I am knocking on wood as well. That's great. Is there anything you would like to see it observe that you haven't seen?
Well, so what's fun about astronomy right now is we're in this era of time domain astronomy. So there's a big group here at Caltech who scans the entire sky every night in the optical, and they find all of the things that go bump in the night. And we do a lot of what we call target of opportunity observations, where someone says, it wasn't part of the big planning stage where we know we want to do that, we can plan that out a year in advance. It's okay, this thing's going off now, and we have to go look at it in the next couple of days. And so there's a lot of cases like that where we're gonna spend a lot of time chasing those things down. There are things called tidal disruption events, where a supermassive black hole shreds a star and gets very bright in X-rays. Most of those things we're just waiting for the right thing to go off. I would really love to see another nearby supernova and go chase those down again. But there's lots of, NuSTAR has a 13 arc-minute field of view, which is about your pinky at your distance, at your arm's length. So we don't see very much of the sky at any particular time. So we spend a lot of time, slewing back and forth. But there's a lot out there to go see. I'm not sure I could pick just one.
Yeah. So. And will the solar cycle, will you be able to observe that change in our own sun?
Yeah. So one thing I didn't put up was that, NuSTAR does look at the sun. It's the only focusing hard X-ray mission in space right now that can look at the sun. And so when I said this, 12 orders of magnitude, the radioactive ash, we get 1 photon every week. And for when we point at the sun, we get 100 million photons a second. And so because all of the blanketing on NuSTAR, we can actually really go study that. And so we actually do that a couple of times a year. We actually coordinate with Parker Solar Probe, which you guys are going to hear about, I think, next week. I can promo that for you. And so, so we can certainly see as the more sunspots are happening on the sun, you see more and more flares. And so we go look at the sun every once in a while to see what's going on there. And that gives you this extra view. We have the Solar Dynamics Observatory, which is great, but it's soft X-rays or ultraviolet. And so NuSTAR is really the thing that tells you if there's particle acceleration going on in a flare and all kind of fun stuff. In addition to the radio emission, all that kind of. There's solar physics is fantastic. I have a lot of fun with it.
I love that. Okay, maybe just one more and then we'll let you go. Let's see. Paula's asking, will you explain a little bit more about how you point the telescope if you don't have any thrusters on there?
Yeah, so most telescopes in low Earth orbit have electromagnets. So you basically have, we're a solar powered observatory, right? So you get the charge from the sun, you can run a current through an electromagnet, and that interacts with the Earth's magnetic field. So just like pushing 2 magnets against each other, you can sort of get them to spin. So the Earth's magnetic field obviously isn't moving, right? But when you're operating in this background magnetic field, you can always point NuSTAR against that magnetic field by adjusting these electromagnets. We've got 3 or 4 reaction wheels on the telescope that point things around, which is the same way that Chandra and XMM, most things that are sort of, not in cislunar space, use these magnetic torque rods to do that.
That is so cool. I did not know that either.
Yeah.
Oh, well, I just want to thank you so much for joining us. It's been a true pleasure. Thank you, all of you who have joined us online as well. It's really great to see so many people here with us. I want to thank everyone for tuning in and just stop the recording quickly, Brian, if you would. The other Brian. Hi, Brian Cruz. Thank you. I'll let all of you know that you can find this webinar along with many others on the Night Sky Network website in the Outreach Resources section. Each of the website pages also features additional resources and activities, and we'll post tonight's presentation on the Night Sky Network YouTube channel. Actually, it should be up there tonight. So you can catch it right there. We'd love to hear a little bit about what you've learned tonight and maybe what you'd like to hear more about in the future. I'm going to stick a link to the Google form in here. If you want to share your thoughts, let's see. Oops, one moment. All right. Oops, there you go. All right. And I encourage you to join us for our next webinar on Monday, August 22nd. Same time, same place, almost same place on the YouTube channel or here on Zoom if you're a member of the Night Sky Network, when Dr. Kelly Korrick from NASA will bring us up to date on the Parker Solar Probe and its explorations of the near sun environment.